we're going to get started on our final chapter. And there are two parts to this, hypothesis test for a single mean and hypothesis test for the difference in two means. These are going to, in lots of ways, be very similar to last week, hypothesis testing. Only difference here is that we're going to be testing, is there evidence that a mean is bigger than this number, less than this number, or not equal to it? So it's going to look very similar to last week, at least in the theory, right? But there are differences. There's going to be a lot more of it done using SOLV, so even less by hand. So let's get started. Let's give you a story that would kind of show you how this works. Suppose that in America, that the average number, some new, of times that people go to a movie was 3 times per month. Suppose that's what it was way back in the 60s, right? So 3 times a month, people would go to the cinema, right? Watch a movie. And the standard deviation, whoops, let's do that later. So that is basically the starting point. And somebody decides that he thinks it's changed. He thinks people are going to the movies less now on average than they did in the 60s, right? So we want to prove, if we can, that the mean is now less than 3. And so they decide to set up a classic hypothesis test to test if this is true or not. And the significance level we're going to use is 5%. And they collect a sample. And it was a sample of 200 people. And they found out that the average was 2.4 per month. Now, superficially, that is definitely less than 3. So that's good evidence that it is, it's gone down. So how do we set up the hypothesis test? Right, so that's basically the beginning. First thing you do is you set up an H0 and an HA. But we are not dealing with proportions here. So the null hypothesis is that it is equal to 3, and that for this particular story, it's less than 3. And you notice it's new that we're using, right? New is the population mean. So we are saying it used to be 3, and the alternate is that the population mean is now less than 3. So far, so good. Now, there's a number of things that we should check before we continue with this. And the first one is it a random sample? These are the kind of conditions that you should check. Just like in a proportion one, shouldn't we check it's a random sample, even although most of the time we don't bother, we just assume that it's all correct. So yeah, it's a random sample. Second one is the size, is it big enough? Now, when it was a proportion one, didn't we use the 10 rule, right? NP0, N1 minus P0 had to be bigger than 10. Essentially, at least 10 people said yes, and at least 10 people said no. But when it's this situation, there isn't an NP thing going on. So it's a really kind of hit and miss here. And I apologize for the vagueness, but you need at least 30 people in your sample. Now, can you do it with less? Yes. If you do it with less, be much more wary of any conclusions you come to, right? So theoretically, you could do it with a size 4, right? But if I did anything with a size 4, do you know I would treat any conclusion with a pinch of salt? I'd say, okay, the math says that it's significant, but I wouldn't give it much credence. Now, the reason I'm saying about 30, you can ask different people and you will get different answers. If some textbooks say 25 or more. Some will say you need 50 or more. You know, some will say this, some will say that. It's very difficult to pin them down, right? Because there's so many different decisions about how much that should be. But basically, if you've got those two, is it a random sample and is the size big enough? You're good to go. In this case, would you agree? We're good to go. And then you will calculate t-score or a z-score. But they're going to be done using SALT. So you won't need to worry about which one. So when do you use a z-score and when do you use a t-score? That's a little bit vaguer. Use a z-score, right? If the population is normally distributed. So if they say to you, we know that the population is symmetric, right? You know the various names, symmetric, bell-shaped, normal, right? It looks like a hill. So if they say, yeah, your data came from sample that looked like that, you can use the z-score. Oh, or technically, you could get away with it if you get very large data, right? If you were doing it with 2,000 or 20,000 people, you could get away with that, but right? So we're talking at least 1,000 when I say very large. Use the t-score most of the time. So unless there's some specific information that leads you to use this, well, you always go and make this your default, right? The t-score. So unless they say, oh, it's normally distributed, or the sample is 1,000, right? Something that's really noticeable, go with the t-score. So let's show you SALT, because that's how you're going to do them all. As soon as I find a button with SALT in it, here we go. Are you looking at SALT right now? Okay, no. What the heck are you looking at? I don't know. Try it again. Are you looking at SALT now? God, this machine drives me crazy at times. Okay, now click inferential statistics. Now I'm going to shrink this up a little bit. It's too big to see what I want to say. Right. Now, when you click on inferential statistics, remember one sample proportion was there and two sample proportion there, right? Isn't that the same place you were last week? So go to the same place this week. Everything you want to do is here, right? And this is a one sample story, boom. Now the sample mean in this story was 2.4. And the standard deviation, because I forgot to tell you, was 1.1. And the sample size was a decent size, it was 200. Hypothesis mean was it used to be 3, and we're trying to see if we can prove it's less than 3. Are you happy about it used to be 3 and we want to see if it's less than 3? That's the sample mean. That was its standard deviation. There's the sample size. And at this point here, you just click generate results. And you see this guy here called the T statistic, right? Oh God, what's my brain like? Remember last week, didn't they call this guy the Z score or the Z statistic? Or I think they might even have just called it the statistic. Remember that guy? Right, he's now going to be called a T statistic, right? Because we're using the T score. And this guy is negative 7.7. And you see the P value is tiny. Right. which is good news. So let's continue back to our story. Since pretty much everything that you need was done by salt, what we now do is we just go and we say, okay, the p-value was 0.00001, or at least less than that. And you finish with your test. And that is the p-value less than alpha? Is 0.00001 less than the alpha? And the answer is yes. And when you get that, you can say there is enough evidence to reject H naught, or to reject the null hypothesis. That's one phrasing. There is enough evidence to accept alternate, or to accept the alternate. Try to think of all the ways they phrase this. Or there is enough evidence to prove that the average movie attendance has gone down. Have you noticed that they phrase this thing so many different ways? You just have to get used to these are all the same thing, just telling you it in different words, right? So there's enough evidence to reject the null hypothesis, or H naught. It's the same thing as saying there's enough evidence to accept the alternate, which is the same thing as saying there's enough evidence to prove that the average movie attendance has gone down. Right, it's less than 3 now. And that's pretty much 90% of what you need to know for this type of question, right? Now, there's a bit of stuff at the start, but a lot of that is overlap, and it's to do with you know, some of the processes in between. To give you an example, suppose I give, maybe I could just use their questions. That might be quicker. I'm going to try that, see if I can do it. Okay, I'm going to just go through some of these early questions before we get to the stuff that you need to use salt. Bear with me for a few moments while I adjust the windows. Try and make things a little bit bigger. Right, so, and now let me put it on so you can see it. Right, you should be looking at question 1. Is that what you're saying, guys? Okay, so it's one of those, explain whether each of the following statements is true. One of the 2 possible conclusions in a hypothesis test is to accept the null hypothesis. Well, that's not true. You never accept the null. You either reject it or you accept the alternate, right? If you don't get evidence to prove that the movies has gone down, that doesn't guarantee that it's still 3. Doesn't that just mean you haven't found evidence to prove it's gone down? Right? It might have gone down, it might have went up, but there's no evidence in that. So you never get to do that. So it's either false that one or false this one. False hypothesis tests could provide evidence about the alternate being true, but not about the null being true. The statement reject the null hypothesis and accept the alternate. Is that the same thing? If you reject a null, is it same as accepting the alternate? Yeah, it's the logic of it. So Both statements would be correct conclusion any time a test approved of it. So it's that one. And here's one, fill in the sentences. Best just read that over. I don't want to spend time when you can just be reading stuff. Oh. They have just found yet another name for all the other guys that I mentioned, and that was not one of my names. Didn't I call it a T-statistic, a statistic? I can't remember what the other ones. They have just found another one, the standardized statistic, right? T-score. So figure out which one of those is the T-score. Right. A botanist for a large rose farm is told that the company currently averages $217,000 in sales annually. Shrink up a little bit. The company hires her to work as an outside consultant in order to increase their annual sales revenue. The null hypothesis is that it's going to just be the same, right? It's still 217,000. Since she wants to improve it, won't the alternate be one of these? Let's do the alternate first. Which of these four is the alternate for she improves the sales?
Greater than or increase?
That's it. Agreed? In fact, aren't that one and that one the other three things, right? Altogether, don't you always prove it's bigger than, less than, or not equal to, right? That's the over here. Bigger than, less than, not equal to. And that's what's happening here. Now, is this called one-tailed or two-tailed? Isn't that really the same question that you've probably done in the proportion ones? Now, a chemist believes that a cornfield must be treated with a fertilizer on average 3 times over the course of its growing season in order to get optimal plant growth. But she's curious about determining if the corn could be doing equally well with fewer treatments. So the null hypothesis is equal. Won't this be, let's see if it can, if I can get the same crop with less. And definitely one-tailed. And that one's similar, so I'm not going to do that one. Okay. Define the parameter of interest and then use it to write a null and an alternate hypothesis in symbols for each of the following questions. Okay, so here's the first one. Many cars have recommended tire pressure of 31 psis. At a roadside safety checking point, officials pick 60 random cars for which they recommend tire pressure and measure what they are in one of the tires. And what they want to do here is they want to know whether drivers on average have too little tire pressure. So the parameter of interest here, right, isn't it the tire pressure, right? That's what we're interested in. In fact, the average tire pressure. Now, the null hypothesis will be H naught, and it's going to be mu equals. So where in this list of guys will I get that funny mu letter? Because we need to type it in.
Greek.
And where are you hiding? There you go, mu, and it should equal 31, right? That's what the story says, and I put minus because I hit the wrong button. Equals 31. Now, up here, have too little pressure is the clue. So what will the alternate be? Greater than 31, less than 31, or not equal to it? I think the little kid gave the answer there because I heard less than. right? Now, remind, in the sentence up here, what do they want to prove, right? Or know, if you want to use that word. They want to prove that there is too little pressure. They want to see if there's evidence, right? Little, lesser. If they'd said they want to know whether drivers don't have that pressure, right? It's different from 31, right? Too much or too little, right? But different. Then I would have used the not equals to in here. In fact, you can't do not equals. Don't you have to do exclamation mark equals? Because that's instead of not equals, and I'm not going to mump and groan about that one. There's another story with the same thing. Now, here you have the null hypothesis, the mean of your sample, the standard deviation of your sample, and the sample size. So that's everything that you need. And all you're going to do is hit salt and find that guy. Okay, so I need to find a salt one. That one will do. And hold on a second. Good. You're going to get dizzy with the number of windows I end up opening here. Right, so we are going to find this guy here, right? The test there. Hey, they used it. They called it the test statistic again. Great. Right, they're back to calling it the test statistic. Okay. So what, I better write these numbers down. I have a mu of 260. I have a mean of 268. I have a standard error of 4. I have an N of 100. So hopefully that is everything I need. One sample T, good. Sample mean 268. Sample standard deviation 4. Sample size 100. And we want to do a 260. And I can't remember what they want us to prove. They don't mention if it's a greater than or a less than. Huh. Okay, so then I will do greater than. Oh, wait a minute, what's the number look like? 268 is bigger. Yep, greater than will work. That's, I guess, how I knew it was that. The mean is 268. Isn't that bigger than 260? So that's why I knew it's greater than. Generate, and there we go. I get the answer 20. You see your T statistic? 20. Okay. And there's a little picture for it. And they've not got 20 because I'm in the wrong picture, right? Okay. Okay, I'm now going to leave that for a while and go back to setting up some of my own questions, and we'll do them from start to finish. So, let's suppose that in the past, the IQ of Americans was 100. And social scientist, maybe a psychologist, thinks that the IQ may have gone down in the last 10 years. Why? Not enough stimulus. Kiddies now get a piece of electronics. Yeah, that's your babysitter. Watch the TV, right? Not getting the stimulus that they need. So they conducted a sample of just 50 people, which is kind of dangerously small. And they found out that the IQ of these people is 97, and that the standard deviation was 5. And we want to see if there's evidence that the IQ has gone down. And we're going to use the significance level of the typical 5%. So the null hypothesis is going to be that the mean IQ is still 100. And the alternate hypothesis is that it is now less than 100. That you would probably be typing in, right? But pretty much everything else is going to be done by SALT. So let's suppose they ask for the test statistic or one of the other 5 names for that guy. And the p-value. And we'll call that A, we've already done. This is going to be B, and C is going to be your conclusion. So let's see what we get. I'm now hitting the SALT button again and doing all that good stuff. And we will go back in and we should be able to, hopefully, put the whole package together. Right, inferential statistics, gotcha. The mean IQ was 100. The standard deviation was 5. The sample size was not very good, 50. And the sample mean wasn't 100. The sample mean was 97. Everything else is good. That guy was the 100. And we want to know, has it gone down? And our T statistic was negative 4.24. Do you see it there? Negative 4.24. And the p-value is right next door, which is 0.000049. Okay. Are you comfortable about how we put all the numbers that we had in that story? Right, all these guys, and how we generated that just by reading the story, but these 2 things came from SALT. Now, conclusion time. You always finish with this test. Is the p-value that you got, is it less than the significance level alpha? Is 0.000049 less than 0.05? Isn't the answer? Yes, it is. That is definitely less than that. Okay, how do you want to phrase the final part? Sometimes don't they give you a little sentence where you pick the word out of the sentence? But since I don't have that, because I created this one, couldn't we just say there is evidence that IQs have decreased? In English, wouldn't that be essentially what the IQ would be, right? They have got smaller, right? They have decreased. And then if that was true, wouldn't there then be, okay, then maybe we should be telling parents that they should be spending more time with their child, right? Doing good old fashioned reading books and playing with them and getting them to interact with other kids, you know, get their language. You know, if you stare at a little electronic machine, you're not going to have a good language skill, are you? Isn't it go and run about with other 4-year-olds and, you know, just increase your vocabulary because you have to talk to people. All of those things are really good because the greatest amount of a child's development happens in the first 6 years of their life, right? That's where all the good stuff happens, or all the bad stuff happens as well. So you want to, I'm sure a lot of your parents should know that. Stimulus is a great thing. I think I was brought up with so many sisters that I had tons of stimulus. Most of it was to try and figure out how to get away from them. I never ever got away with anything. You know, it's like living in a communist country. There was 6 spies watching me. So when I was a kid, there was we call it a swing park. I know what you call in America. You know, it has roundabouts and chutes and things. So it was right next to where I stayed, but it was across a main road. And so I was never allowed to go on my own. I could only go, you know, if my parents took me there. But when you sat and when you came out of my house, you could see it. It was like a big ice cream. And no, anytime I even made a movement, one of my sisters, no, Donald, can't go there. Such and fresh and had to go the other way. Yeah, it's not fun. Trust me, having 6 sisters, it's not fun. Isabel, you're laughing like it sounds like that would be fun.
I understand from being the youngest of a couple of things.
So you had a couple of spies watching you? Yeah. Maggie, you have a couple of spies?
Yes, definitely.
Okay. Not fun?
No, not fun.
Where are you, when you in the scheme of things? Brandy, were you a spy or were you being spied on?
I was the oldest of 5, so
you were the spy. You just made sure the kids never did all the things that they were not meant to. You were looking after them. So
yeah.
So it wasn't you were doing a bad thing. You were doing a good thing. Okay, well, that's basically that story. So I'm going to pick one now from them, right? It's got a lot of reading, so I'm not going to back and forward. I'll just give you the gist of the story. It's back to the tire story. Remember the one about the PSI? In an earlier exercise, they went and posed this question. Many cars have a recommended tire pressure of 32 this time. Okay, so 32 it is. Make sure I'm writing this down. Yes, I am. A roadside vehicle check stopped 65 cars. And they found out that the average on those cars was 29.9 PSI, and that their standard deviation was 3 PSIs. And they want you to see if there's evidence that that is actually less than it should be, right? So, H naught and HA. The null hypothesis is that average is still 32. Right? The alternate is, can we prove that it's actually typically less than 32? You know, they said, is there evidence to prove that it's less, right? Would you agree that that's definitely pointing at being less? So that would be, well, they don't call it question A, but I'll call it A. That's what you put into the thing. Now, the next 2 things are the guys that we are used to. They're asking us to find the test statistic. I'll put the answer there when we get it. And the p-value. Okay. And I should be able to, this is the point where I'm going to nip over to, here we go, and show you salt being used. Have you noticed that in none of these questions, there was any reference to being a Z-score? Right. None of the samples were huge, and nobody mentioned it being normal. So work on the assumption that it's T, and you should be fine. Now, I hope you're all looking at salt right now. And in this story then, 1 sample T, the mean that they got was 29.9. Before I finish this, do you think that's going to work? Do you think that's going to be evidence, or do you think it's too close to 32? You got a gut feeling yet?
I think it's too close.
Okay, I don't know. But I certainly don't like 65, right? Because I think that's going to make a difference. Now, here, is it 32? And can we prove it's less than? So are you comfortable? 1 sample, sample mean, standard deviation of sample, sample size. It's null hypothesis 32, alternate, can we prove it's less than that? Generate results. And the t statistic this time is negative 5.64, and the p-value is at less than 0.00001 guy. So I'm going to return back to the whiteboard. Right. There's your t statistic. There's that guy. You might want to do 0.0000 or something, because they always say to 4 decimal places or something, don't they? So that number is exactly that number, right? Well, oops, we are ready for conclusion. Right. So I'm going to show you what that looks like in WebAssign. Would you agree that that p-value is less than 0.05, right? So we have the evidence. We just have to figure out how they want us to do it. So are you looking at this guy p-value? Okay. On the basis of this p-value, which I'm going to call 0.000, right, to 4 decimal places. Do not reject the null. Do reject the null. Do not again. Reject the null. Reject the null. So we're going to reject it, and that's because it was smaller than 0.05. And what conclusion, in words? We can conclude that the average, see, isn't that the sentence that would make more sense to a human? And it's one of those pick one of two choices, right? Is this beginning to feel a little more deja vu? Like it's mostly the same as last week, right? It's a t-score and it's a mean, but the gist of it is still the same. Right. Which one shall I do next? This is question 15. You looking at it? Right. A herd of 1,500 cattle. That's a pretty decent sized sample, isn't it? 1,500. So I'm just writing this down because it may disappear. And it's 1,500. And was fed a special high protein grain for a whole month. Normally they would do that just before it's time to slaughter, right? To try and get the weight up so they can get more money. A random sample of 40 cattle. Oh, I take it back. He only took 40 as a sample. Was weighed and had gained on average 7.4 pounds. Okay, so it looks like it might work. If the standard deviation of weight gain for the herd is 5.3 pounds, okay, I've wrote that down. Test the hypothesis that the average weight gain for a cow for the month was more than 7. So the null hypothesis is that it's 7, and the alternate is it's greater than 7. And I'm assuming that the 40 that are weighed, even if you never gave them the same grain, wouldn't the cattle just gain 7 pound a weight, just be eating hay like they were always going to get, right? So I guess that's why that's there. So all the numbers I need should be here. Yep. So let's find that guy. And the sample was 7.4. And standard deviation was 5.3. And there wasn't that many, there was only 40, which is getting really dangerously low. This fella was 7, and we're trying to see if we can prove that it's greater than 7. Are you comfortable about the numbers in the setup here? So I generate results, and okay, we got a test statistic of 0.47 and a p-value 0.3. So I'll put them in a minute. There's the test statistic to 2 decimal places. And using technology is basically using salt. And 4 decimal places, 1, 2, 3, that one becomes a 9. Okay. Now, is this p-value less than 0.05? No. So that means then we'd fail to reject the null, right? You fail to reject the null, one of the many ways they phrase it. And we would fail to reject to the null. This means that on the basis of the evidence, you can conclude that was no more. No. There, that's the answer you're going to use. You fail to reject the null hypothesis. This means that on the basis of the evidence, you cannot conclude that the mean amount of weight gain was more than 7 pounds. That's all you can say. You don't know if it was even a weight gain. Okay. Do we have time for this last one? No. Okay. I'm going to do something else. Give me a few moments. While I'm doing this, why don't you, don't go away yet, but put in your last name. So, you know, when we're finished this, you're basically, you're good to go. I want to make sure that I've given everybody a lot of opportunity. Right, I'm ready now. So hang about while you're doing that, and I'm going to show you this guy. We all looking at Math 146. Right, I'm going to go student view, which is dangerous, but I'm going to do it. If you use this second one, right, well, this is one I made eventually to work. Here you will find the 4 questions that you need to get some extra credit. You will get 10% added on to your worst test, the worst one you're going to keep at least, because you get to drop 2. I think I'm just going to add it to the total. That's easier, but it's equivalent to that. And if you get them all correct, you'll get 20% added on to one of your tests. So you could actually get more than 100%. There are 4 questions. Here we go. You only have, well, it says you have a single attempt, I guess, in the sense that I only get one answer from you, because that's the way it's working. And here's a story. Write down the null and alternate. Tell me the t statistics and all that. You're going to use SALT for every one of these questions, I would suppose. There's question 2. There's question 3 and question 4. The points can is not for your benefit. This data is going to be sent to one of our other statistics professors, and they're going to analyze how well people are using this. Okay, so you don't need to get it all right to get your 10%, but at least attempt to do them all, right? Because you are getting something for it, so you should at least, you know, give us good data by actually really doing the question as best to your own ability, that is. And you've only got until midnight tonight. That's the cutoff date. That's when one of the professors, not me, will be collecting the data and sending it on to her. Okay. Last question. When is the final?
Next week.
Correct. Specifically, what day next week?
Monday,
No.
Tuesday.
Oh, we're not doing that game. Right. Next day, I'm going to ask you again, and you are going to find out. And you will find out by looking at the syllabus. And you will find on the syllabus, it will tell you when it is. And I'm not going to tell you, because if I tell you, you'll have forgotten again. Because I did tell you once before. I know it was week
Thursday?
1. I'm not telling you. It might be, it might not. Go find out. and tomorrow.
It's on Friday.
Yeah. Yeah, sometime next week, and it's not Monday. That's all you know right now. Okay,
Is the final on the whole everything we've learned or just the second half?
everything.
Hmm.
Okay, bye-bye for now, guys. I'll hang about for any questions.